Hey, what's up you guys? You are watching the Kaggle code review show and my name is Ilerian Garbazov. Today we'll do the Kaggle competition. The name of the Kaggle competition is Sarcasm Detection. Let's do it together! Guys, thank you for watching my video, and if you like it, push the like button, subscribe and give me a comment which code or which competition I can review for you next. Okay, let's dive in and view the dataset. Past studies in sarcasm detection mostly make use of Twitter datasets collected using hashtag-based supervision, but such datasets are noisy in terms of labels and language. Furthermore, many tweets are replies to other tweets, and detecting sarcasm in this requires the availability of contextual tweets. To overcome the limitations related to noise in Twitter datasets, this news headlines dataset for sarcasm detection is collected from two news websites. The Onion aims at producing sarcastic versions of current events, and we collected all the headlines from news in brief and news in photos categories, which are sarcastic. We collect real and non-sarcastic news headlines from HuffPost. The dataset consists about 28,000 text data points, where each data category belongs to two categories, sarcastic or non-sarcastic. We will use two models for making predictions, word-to-vec and GloVe embeddings. We will then compare the results and see which performs better. First of all, we need to import libraries, so we would import NumPy as for the linear algebra, import pandas for data processing, import OS to write data to our path. We would import other libraries: NumPy, pandas, Seaborn, Matplotlib, Seaborn and Matplotlib for plotting, NLTK, and I would have a talk on it a little later. As sklearn preprocessing, we would import label binarizer. We would import different from NLTK. From word-to-vec, we would import word cloud and stop words, and all the stuff from the NLTK. From BS4, we would import beautiful sub, and I'll talk about this a little later. We would import rare, string, Unicode data. From Keras preprocessing, we would import text and sequence. From sklearn metrics, we would import classification report, confusion metrics, and accuracy score. From sklearn model selection, we would import train test split. From string, we would import punctuation, import Keras. From Keras models, we would import sequential. From Keras layers, we would import dense, embedding, LSTM, dropout, bidirectional, and GRU. And we would import TensorFlow as TF. Then we need to load the dataset. We would read the dataset with pandas, and here it is. So we've got the label in the column is sarcastic 0 or 1, the headline of an article, and the article link. Let's check, do we have null values? So after the checking, we see that we got zero null values in our rows, and we can delete the article link column. So let's see the head of our data frame. Here it is sarcastic, and the headline. We can see. We can count plot our rows and see that the dataset is balanced. What are the stop words? Stop words are the English words which doesn't add much meaning to a sentence. They can safely be ignored without sacrificing the meaning of the sentence. For example, the words like the, he, have. Such words are already captured as this in corpus named corpus. We first downloaded to our Python environment. So we'll take all these stop words to stop and the punctuation and update from a string dot punctuation and update our dictionary of stop words with punctuation. So then we need to clean the data, and we'll do the basic data cleaning. We've got a few functions. We would define a strip HTML and take it from the beautiful sub. We would remove the square brackets from re.sub. We would remove URLs from re.sub. And removing the stop words from text. Do you remember in the previous step we got the dictionary of the stop words, and we would remove it from text. And we've got the we'll combine it and make the function denoise text, where we would use strip HTML, remove between square brackets and remove stop words that we have defined, and apply this function on review column. Apply denoise text. And right now I'll give you a short description on this maybe new for you libraries. Beautiful Soup is a Python library for pulling data out of HTML and XML files. It works with your favorite parser to provide idiomatic ways of navigating, searching, and modifying the parse tree. It commonly saves programmers hours or days of work. These instructions illustrate all major features of Beautiful Soup, and I'll give you the link to this Beautiful Soup documentation. See it in the description. So the main that we're pulling data out of HTML with the Beautiful Soup. RE means regular expression operations. This model provides regular expression matching operations similar to those found in Perl. Both pattern and strings to be searched can be Unicode. Regular expression use the backslash character to indicate special forms, and the solution is to use Python's raw string notation. And it's important to note that most regular expression operations are available as model level functions and methods on compiled regular expressions. After we denoise the text, let's see the word cloud for text that is not sarcastic. We would use word cloud library, and I will give you the link and the short summary on it a few months later. So let's see the word cloud for not sarcastic. You see the main words: Trump, Donald Trump, news, say, way, year, take, make, American. So it's the main word cloud for not sarcastic. And the word cloud for sarcastic text, it's label 1. Man, you, area, man, report, Trump, steal, time, woman, nation, make, American. It's for sarcastic. You saw the word cloud. Word cloud for Python. Here you would find instructions on how to create word clouds with Python. Word cloud project. And I'll give you the link on it. So it gives you an opportunity to make beautiful visualization. Let's look for some numbers of characters in text and see the different distributions. So here is a code for histogram on characters in text. You see that we got different distribution on sarcastic text and not sarcastic text. Number of words in each text for sarcastic text and not sarcastic text. And let's look on the average word length in a text. So we would build the histogram distribution plot, and you see that we've got pretty the same distribution on average word length in each text for sarcastic and not sarcastic. And here we go, we can start the modeling part, and we would start with the word to vec, and let's do the introduction to word embedding. Word embedding is one of the most popular representation of document vocabulary. It is capable of capturing context of a word in a document, semantic and synthetic similarity, relation with other words. What are word embeddings exactly? Loosely speaking, there are vector representations of a particular word. Having said this, what follows is how do we generate them. More importantly, how do they capture the context. Word to vec is one of the most popular technique to learn word embeddings using shallow neural network. It was developed by Thomas Mikolov in 2013 at Google. Why do we need word embeddings? Consider the following similar sentences: have a good day and have a great day. They hardly have different meaning. If we construct an exhausting vocabulary, it would have like this: have a good and a great day. So it would be the vocabulary for all these two sentences. Now let us create one hot encoded vector for each of these words. And at the end, if we try to visualize these encodings, we can think of a 5-dimensional space where each word occupies one of the dimensions and has nothing to do with the rest. This means good and great are as different as day and have, which is not true. Our objective is to have words with similar context occupy close special positions. Mathematically, the cosine of the angle between such vectors should be close to 1. Here comes the idea of generating distributed representations. Intuitively, we introduce some dependence of one word on the other words. The words in context of this word would get a greater share of this dependence. In one hot encoding representations, all the words are independent of each other, as mentioned earlier. Let's do the word to vec part of our kernel. So converting text to format acceptable by Gensim. Gensim is a library. And I'll give you some shortcut on it. Gensim, a Python framework for fast vector space modeling. Gensim is a Python library for topic modeling, document indexing, and similarity retrieval with large corpora. Target audience is the natural language processing and information retrieval community. Let's see how it works. First, we'll do the words dictionary of our text. Importing Gensim, the dimension of vectors of our dictionary would be 200, so embedding dimension is 200. And the next step is creating word vectors by wordvec method. So we are from Gensim, we take models, word to vec, take the words, give the embedding size, and our vocabulary size of word to vector model would be 38,071. And each of these words would be represented with our embedding dimension. We would use Keras tokenizer. This class allows to vectorize a text corpus by turning each text into either a sequence of integers, and we are using a tokenizer with the number of words 35,000. We feed it on our words dictionary and use text to sequences, and X would be sequence, path sequences, so tokenized train, and with max length 20. and we are adding 1 because of reserved 0 index. Embedding layers layer creates 1 more vector for unknown words or padded words. This vector is filled with zeros. Then we would do function to create weight matrix from word2vec GAN-SIM model. Here is the code, and it's not that hard. And after that, we're getting embedding vectors from word2vec and using it as weights of non-trivial keras embedding layer. So embedding vectors are get weight matrix, word2vec model, and tokenizer word index. Now we can define the model. So we're training word2vec model. So let's define neural network model sequential. We would use sequential from keras, and first layer non-trainable embedding layer. So we're adding embedding layer. Then we would use LSTM, bidirectional LSTM with 128 units, recurrent dropout 0.3 and dropout 0.3, and we would return sequences. After that, we would use bidirectional GRU with 32 units and the recurrent dropout 0.1 and the dropout 0.1. And we would cover this with a dense layer with 1 neuron and sigmoid activation function, because we got 2 classes. And we would compile the model and see the summary of the model, and we would compile it with the Adam optimizer and the learning rate 0.01 with the binary cross entropy loss and accuracy as the matrix. And here you can see the summary of the model. So we got total parameters near 8 million. All the parameters are trainable. After that, we are splitting our dataset on test and train split with a test size 0.3, fitting our model with train examples and batch size 128, and the validation that we've got from the train test split. And after fitting the model, you can see that loss is decreasing and accuracy is increasing, and we've got pretty good accuracy, 0.9 on the 3rd epoch. And let's see the history. Evaluate the model on the train and test dataset. And the accuracy of the model on training dataset is 99.69, and on the on testing data is 79, and it seems that we overfitting. Let's see. Let's plot the history and analysis after training of. Let's do the analysis after training of word2vec model. On each epoch, we would plot accuracy and loss on training and test dataset, and you see that seems like the model is overfitting and not performing well on test data, because here is training accuracy and test accuracy. Test accuracy is going down on 2nd epoch, and the loss is going up. And we can plot the confusion matrix, and you see here is the confusion matrix. And that was a word2vec model on sarcasm detection. And if you like it, push the like button, subscribe to my channel. And if you want me to show you another model, GloVe model, push the like button and give me a comment. I want to see the GloVe model, bro. Thank you, guys. Thank you. And the dataset was provided by Rishab Misra. It's an ML engineer at Twitter from San Francisco, California. Thank you, Mr. Misra. I found this kernel at Maths 2000. It's a student at Netaji Subhas Institute of Technology, Delhi, India. Thank you, Maths 2000. Thank you. See you tomorrow.